B.S.Abdur Rahman University, earlier known as B.S.Abdur Rahman Crescent Engineering College.
Good afternoon to one and all present over here. The topic what I have chosen to take is DC generators. And before going to the topic, let me just put a few words about me. This is Mr. Shanmuga Priya Sundaram from B.S.Abdur Rahman University, and I am a part of EEE department of our university. And going towards the topic, DC generators. What is a generator? What does it do? So can you tell me from the term generator, what is that? Generates what? What type of quantity it is generating? Can I just tell generates power, but what sort of power it is generating and how the energy conversion is taking place inside a DC generator, and what happens that after energy is getting generated, how it is going to get converted and how it is going to work. All these things we are going to look in this video. So going to this working principle. A generator, a very basic definition for a generator, it converts a mechanical energy into a electrical energy. So this principle of electromechanical energy conversion is based on a law which has been put forward by a scientist called Faraday's law. That's otherwise called as the Faraday's law of electromagnetic induction. So what does it say in this law? That is, whenever there is some flux which has been associated with a conductor, and that conductor is going to cut the lines of flux, lines of force which has been produced by the flux, you get an induced EMF, and that induced EMF, I say that as a dynamically induced EMF. And going towards the construction of a DC machine. So what is there are some 6 important parts which explain the parts of a ideal or a practical DC machine. So what are these parts? So looking over here, you can see a yoke. So what is that yoke? A yoke will serve as so these are the 6 important parts which I have which I have told previously, and this is a cross-sectional view of a DC generator. So that was a practical view, like how does it from the front view, and this one is a cross-sectional view. And what is this yoke? The yoke is nothing but a frame or a mechanical support for the machine. It's also act as a protecting cover or a protecting part for all the rotating machine, which protects it from the dust or moisture, and it's made up dust and moisture, etc. And next is, can you just look over, there are some 4 poles which has been present inside this machine. For illustration purpose, I have taken a 4-pole machine. It not necessarily have to be a pole. So basically what is this pole is called as? A pole of a generator is an electromagnet. That is, it has got a coils which has been wound around these poles. So what is this coils are doing? Whenever I give a current, that is I am exciting it, these coils produce a magnetic flux, and this flux passes to our armature. So what is this armature? Next part, what is this armature called as? So armature is nothing but a rotating part. If you look at the armature, this is a separate view of a yoke, and this one is a pole core and the pole shoe. So next thing is, what is this pole shoe? The pole shoe is nothing but the extended part of the pole core. So what is the purpose of using this pole shoe? Why do you need a pole shoe? That is, I told you that when a field winding is excited, the field winding which is wound around the pole is excited, it spreads a magnetic flux. So but there should be some extended portion in order to take this flux and put it in the travel towards air gap and then reaches the armature. Our pole shoe serves this purpose. The pole shoe is nothing but an extended or enlarged area of the pole core and the pole. Alright, and next thing is, so this is an internal view of how this pole and the field winding is being wound up. And next thing is the armature core. So what is meant by armature? So armature is nothing but a rotating part. If you look at the armature, you can see some slot and the teeth which has been put around the armature. So you can see there are some conductors which can be placed inside these slots. So all these armature conductors interconnected to form a armature winding. If you look at there are 2 types of armature windings. One is a lap winding, other one is a wave winding. And next thing is a commutator. So why do you need a commutator? I told you that the EMF what is being induced in a generator is a dynamically induced EMF. The EMF what is being induced, it will change from instant to instant. That is, you can look, the EMF changes from positive to negative. So what we get is an alternating EMF. I want to convert it to a direct current. I want to convert it to a direct quantity. So I need some equipment which would serve the purpose. So I am taking a commutator which can act as a mechanical rectifier where it can convert an alternating quantity into a direct quantity. And commutators also serve another purpose called as current carrying devices. That is, which current, from where the current it is being carrying. That is, it takes a current from the armature conductors. We know that Faraday's law of electromagnetic conduction. Whenever a conductor is rotating and it cuts the lines of force, an EMF is induced. So what is rotating over here? Our armature is rotating over here. Already the flux has been produced by the 4 poles which has been present in the machine. So once the lines of force has been cut, you get some induced EMF, and there is some quantity which has been induced. I want to take this quantity and give it to my external circuit. So I need some device which can act as an ambassador or which can act as a carrier to carry this particular quantity and give it to my load. For that purpose, I am going to a device called as a commutator. That is, it carries the current from the armature conductors and give it to another part called as a brushes. A brush. Why do we? The next thing, why do we need a brush? For the commutator has taken the current. What is been it has taken some quantity. What is been induced in the armature conductors, and now the brushes is going to take the current carrying part from the commutator and give it to the external part. And going to the working principle. So how does this DC generator in general works like? In order to explain the concept, let me for the illustration purpose, I am taking 2 poles, that is 2 electromagnets. One is a north pole, another one is a south pole. So you can see, since it's a north pole, you can see the magnetic lines of force starting from the north pole and ending at the south pole. So let you imagine that this is a rectangular conductor which has been, imagine there are some 2 magnetic poles which has been kept apart. So now my conductor is in my conductor is in the flat position, and I am making I am exciting the conductor. For this I have taken a single turn conductor. Not necessarily it has to be a single turn. You can take even a 2 turn conductor or a multi turn conductor. Now I am exciting this conductor with any sort of supply and making that conductor to rotate. Once the conductor starts to rotate, what happens here? It starts to cut the magnetic lines of force. Initially, that is when the conductor is at 0 position, there is no cutting of lines of force. Why? Because the rectangular conductor, it is parallel to the magnetic lines of force which is flowing from one pole to the another pole. So what does our law says, like whenever there is a change of flux, that is whenever the magnetic lines of force is being cut, you get an induced EMF, and that induced EMF is constant with respect to time. And if for this I am taking I am going to plot a graph so that to understand what is the proportion of the EMF induced with respect to the time taken. For that I am taking initially at 0 position. Let me assume that the time theta degree as 0 degrees. At 0, my rectangular coil is in parallel to the lines of force. No EMF is cut. It is at 0. And now let me turn it to the clockwise direction. So let me assume that particular angle as 90 degrees. At 90 degrees, can you see that this rectangular coil has become perpendicular to the lines of force? So when it is becoming perpendicular to the lines of force, obviously it will try to cut the lines of force which is trying to flow from north pole to the south pole. So once it is cutting the lines of force, what happens? The EMF induced is maximum. So that you can get the point which has been denoted as 3. So let me take another revolution called theta is equal to 180. That is, I am going to rotate it and keep it at 180 degrees. What happens here? Again my conductor has become parallel to the lines of force. There is no cutting of lines of force which has been taking place, and EMF induced is 0. And next let me take to another position called, so can you just this is from 0 to 90 degrees, and this is at 90 to 180 degrees. And now I am going to talk about the phase reversal which has been taking place. So this phase reversal, it will be the device which performs this phase reversal is actually the part called as a commutator. So after 180 degrees I am going to rotate the conductor in the anti-clockwise direction. In that case what happens? It is going to get reversed, and once it is becoming at 270 degrees, it is perpendicular in the opposite direction. There is maximum cutting of lines of force, and the EMF induced is maximum over here. And next at 270 to 360 degrees, another 90 degrees rotation I have taken. At 360 again the phase reversal, that is it has become parallel to the lines of force, no cutting of lines of force has taken place, and EMF induced is 0. You can see it at the end. So the EMF what is being induced is changing from instant to instant, that is was alternating between positive and negative of cycle. So I say that EMF as a alternating EMF. I want to convert it to a directional EMF, I go for a commutators. And the applications of DC generators or battery charging, and for DC locomotives for regenerative braking, and for used as a voltage boosters. Thank you.